Good morning, everyone. As Steve's just mentioned, my name's Helen Pendlowski, and I am chair of the Clay Minerals Group, which is a special interest group of the Mineralogical Society of the UK and Ireland. And we're delighted that you've all joined us here, both on remotely and in person here in Dublin. It's my pleasure to introduce the first plenary speaker of this conference, which is also the 26th George Brown Lecture. So a bit of background on that. The George Brown Lecture is given by an individual selected by the Clay Minerals Group Committee, who's a clay mineralogist recognised as an authority in their particular field. This lecture is then also published as a review paper in Clay Minerals. So we hope that you will also get to see that later on, maybe this year, possible. This year, the Clay Minerals Group Committee has selected Dr. Stefan Kaufhold to receive this honour in presenting this prestigious lecture. Since 2002, Stefan has been based at the BGR, the German Geological Survey in Hanover, Germany, and has significant experience both in research and industry working with industrial minerals, with particular emphasis on swelling clays and their performance as barrier materials. Stefan's contribution to the clay community includes around 166 first papers, publications, which rises to over 200 when including those as co-author, and sees almost some 4,500 citations. So definitely a significant person in this field. 7 of these publications are from the first half of this year alone, including a book that has recently been published titled Bentonites: Characterization, Geology, Mineralogy, Analysis, Mining, Processing and Uses. If you're lucky, you might see a copy of that book somewhere during this week. I'm sure it's going to become a significant reference. So his lecture today will focus on an area which is a current priority in many countries, and I'm sure it'll have something for everyone here to enjoy and engage with. And hopefully there will be lots of questions following Stefan's presentation. So please join me in welcoming our 26th George Brown lecturer, Dr. Stefan Kaufhold.
Just that you can hear me better. So we tested it before. Isn't it great? Okay, well, I can start anyway. We will have a picture sometime, I think. Thanks, Helen, for this really kind introduction. It's always difficult to find words after such a kind introduction, but yeah, well, at least the numbers are correct. So I'd like to thank the Clay Minerals Group for giving me the chance to open this incredible conference. Obviously, the last international clay conference, so I have the honor to open the last international conference. This will be definitely written on my grave. So really, thanks a lot. I can't express how honored I feel, and yeah, I have to do something special today. That is what I decided. And you will see that afterwards. So I could have taken the chance, actually, to talk about this book, which was mentioned. I will find some words maybe concerning this book. Steve and Helen already said that maybe there will be a printed copy lying somewhere. If it's not from the editor, then it's Steve's personal printed version. So leave it where it is. Otherwise, you will ever see in the first page, it was his book, right? Don't take it with you, just take a look at it. So what will you find in this book? Actually, there's a lot of data, really. So I call these samples that we investigated in this book our main actors. So there are 38 bentonites and 2 illite smectite clays, which were also considered in the frame of barrier research. So that is why we included them together with the bentonites, just to have an idea of how they perform for example, in terms of rheology or swelling. So that was considered to be interesting. But you will find a lot of data of 38 bentonites from all over the world. You will find description of methods. You will find discussion of methods, limits, limitations, and possibilities of the methods. You will also find a couple of really nice pictures inside, because a lot of people contributed to this book, and Albert Gilk, who's here, and Michael Dörschuk, who's unfortunately not here. I guess they have seen more than 90% of the world bentonites. So they shared all these great photos from their minds, from processing, from exploration and whatever. That is quite interesting to see. And those pictures, was that me? No. Those pictures can, of course, also be used for teaching as well, to show the students how different the mining of bentonite is when you consider different sites in the world. Well, you also find a lot of experience from industry, because that was important for me. Helen said that I spent some time of my scientific life in bentonite industry, so I saw this site as well, and I recognize that there's so many experience in the industry, and scientists working for the industry, but they never write that. They are not used to writing. They're not writing papers. They're not writing books. So this is all experience which is lost, right? And my idea and intention was to say something of this experience. So I invited a couple of specialists from industry to write down their experience, and you will find that as well in this book, right? And when we started, actually, then I thought that I would not consider bentonite formation, since that was done by Grimm and Grüven, and so I'm not an expert for that anyway. So I decided to leave out the formation, and then Albert said to me, "You can't leave that out. I will write this chapter," and he did it, and it is the first one, and it's actually that one which is online accessible, so that is open access. If you're interested in bentonite formation, you even don't have to pay for that, right? And I'd like to take the chance now to thank all these the co-authors. So such a comprehensive compilation can only be done if you have a lot of really experienced people around. Some of them are here, so we can celebrate the final publishing of the book, maybe with 2 or 3 beers afterwards, but the others are also acknowledged as well. A big thanks to all of them. Without you, it would have been possible. But I decided to do something special. That's what I announced, and that's what I'm going to do. I will not talk about bentonites. I will talk about claystone, right? And when it comes to claystones, we can start the discussion already with the term claystone. I remember back in March in this year, we had a DTDG workshop in Krakow, which was actually great. And I remember the talk from Lawrence Warr, and he suggested that the correct term for everything between a mud and a schist would be mud rock. But actually, I didn't really like this term. So claystone is probably closer to the German word Tonstein. And if you look up the papers, that you find claystone actually more often compared to mud rock. So I decided in this talk and in this study, which will hopefully publish then someday, to use claystone. But that could be the first point we could discuss. Well, I remember times where awarded lectures were not discussed. I don't know what happened in between. Something happened and I wasn't there, but today, obviously, they are discussed. And I really appreciate that. So I actually left some time for a discussion, and because there's so much experience outside there in front of me, actually, so that I really appreciate any suggestions. So if there's somebody in the audience saying the claystone is definitely the wrong term, then I would like to know that and take it home, right? Okay, so probably the first point to discuss. The title of the talk is about comparison of claystones as potential host rocks for radioactive waste. It's also already a quite long title, and you can see here all the co-authors. Such a let's say, important and broad topic can also only be dealt with if you have a lot of specialists from different fields. And that is why I listed all the co-authors here. And since this is an ongoing project, we already revised the title. So the title meanwhile reads, A Review of Burial Depth-Depending Properties of Claystones and Implications for Assessing Their Suitability as Host Rock for Encapsulation of High-Level Radioactive Waste. There's probably close to the maximum of words in the title, I'm not sure. But this then up to the reviewers, we will see that. Anyway, it is precise now. That is actually what I'm talking about. But basically, I would just try to compare barrier properties of claystones. It could be that short if you wanted to, if we wanted to. That is the basic situation. We do have a lot of high-level radioactive waste in Europe. We all know that. We all know that there's a favorable solution for that, underground storage, and in different countries, different host rocks are envisaged. Like in France, Switzerland, and Belgium, it will be claystone. Sweden and Finland, crystalline rock, in combination with bentonite, as you guess, I guess you know that. In Germany, we are still open. We are considering all possible host rocks like salt, claystone, or even crystalline rock. We haven't taken any decision yet. So we are in the stage where we have to compare different host rocks. That is why I'm talking about this topic right now. Since 2017 in Germany, we have a law, the so-called Standortauswahlgesetz. So this is like a site selection law. And that says that we have to go for the best repository, not a suitable one, not anyone, for the best. And that means we really have to be able to compare all the rocks with each other. We even have to compare salt with claystone, claystone with crystalline rock. But before we can do that, we have to be sure that we have the perfect salt site. So it is quite a difficult task. And unfortunately, a lot of specialists in Germany are working on that field. And there's a lot going on there. A lot of information is gained. Drilling is going on in Germany. And new data, right, is then generated. So that is the good side of that. That research is going on and knowledge is improving, definitely. So I would talk, of course, not talk about salt and not a crystalline rock, since we are on a clay conference. So we talk about the claystone. And now let's start. In 2016, Rainer and me published a paper about comparison of bentonite. So there was, in a way, similar. We wanted to find the best bentonite for a geotechnical barrier, right? So when you do that, when you try to compare something, you first have to define parameters, the most important parameters, or in industry, you call that the quality determining parameter. And first you have to find all of these parameters, and then you can decide which one is better there or more important than another one. So first I list all the parameters that we think are important parameters for claystone host rock. I sorted them according to the burial depth. So you will see arrows here, and the arrows have colors. And if it's getting green when it's going down, then it's obviously improving with burial depth. And if it's getting red, then it's the opposite, right? So mechanical strength obviously increases. Thermal conductivity. The paleo-temperature, this is the maximum temperature the rock experienced. And it's a quite reasonable assumption that nothing will change if the temperature of this host rock will reach this temperature again, because millions of years before nothing happened at this temperature. So that is a quite good criteria for determining the maximum thermal load the host rock can undergo. Porosity, of course, is getting down. It's important because that translates into hydraulic conductivity. Then we have colloidal detachment, also a possible way to transport radionuclides. Microbiology is not good. It should go down. Ductility, that is, or plasticity, maybe would have been also a suitable term. Adsorption, retention capacity is going down, and there's an open field for swelling capacity. I could not decide about swelling capacity, and we will see why that is later on, right? So let's go into the details. First, literature data. You can see here the parameters listed against each other, plotted against each other, and all the numbers, they stand for a publication. So these publications were then plotted here according to the parameters they are considering. And you will find that most data is, of course, from hydrocarbon industry or in relation to hydrocarbon research. And that then translates into paleo-temperature, vitrinite reflection, maturity parameters, because those are important for the hydrocarbon industry. And even the production, like porosity, permeability is considered. But you will not find a lot about mechanical strength, diffusion, swelling, thermal conductivity. Much less is available there. So we have a quite heterogeneous picture here. Let's go into the details now. Mechanical strength. There's some information available. It is published that mechanical strength increases. That's what we expected. Upon diagenesis or upon mural depth, whatever you like. But we also know that mineral cements, microstructure are important. For example, the way the carbonates occur in a material are important. If they form the matrix, you have a very solid material. If you have them as shells or as fossils, then the opposite is the case. But on average, when it goes down, when the mural depth increases, you will have a higher mechanical strength, and obviously that happens until a certain limit. And that is an important fact to keep in mind, because we will need that later on again. Thermal conductivity. Not much is known about thermal conductivity, because of course we know about porous systems. In porous systems, the thermal conductivity is determined by the matrix and by the pore filling. In that depth, we can assume that their system is water saturated, so we have a two-phase system. And the quartz content may play a role, since quartz is much more conducting, thermal or heat conducting. So finally, we know that for shales or claystones, the thermal conductivity is between 1 and 1.5, right? Anisotropy is also to be considered. But overall, since the porosity is reduced upon diagenesis, upon mural depth, it is increasing with mural depth, right? Paleo-temperature, it's the same. We know according to the geothermal gradient, which can be different, of course. So the thermal load in 1,000 meters can be different from site to site, but it will at a given site be higher with an increasing mural depth, right? Now coming to porosity, is quite a bit of data plotted here, and you can see that it in a way behaves similar to the mechanical strength we've seen before, that at a certain depth, obviously, porosity changes are not that significant as before. And the same holds true for the pore size. You can see this here. Obviously, at 2,000 meters, nothing really happens anymore, or no significant changes occur anymore. And that then translates into hydraulic conductivity. There's a lot of information available, as you can see here. So a lot of papers and information are summarized in this plot. Even the different known host rocks, like the Callovo-Oxfordian boom clay, are included. We of course know that the hydraulic conductivity decreases with increasing depth, and the different pathways, they may depend on the clay content. So if you have a higher clay content, then of course you will be on the lower side of hydraulic conductivity, and low clay contents will result in the opposite. Colloid detachment, the colloids we expect would be then probably smectites with a minimum size or maximum size of 50 nanometer about, and not much is published about that, maybe because it's not significant anyway. We would expect the smectite content to play a role. We would expect the exchangeable cation to play a role, but we would also expect that the exchangeable cation is rather calcium than sodium in the system, in these natural systems. So obviously it does not really play a role. With increasing mural depth, we can fix that less smectite is there, the less fissures are there, and the pores are getting smaller than the size of the smectite. So if the pores are less than 50 nanometer, then you won't be able to move a 50 nanometer smectite. Simple as that. Maybe that is the reason why not as much published about it. I don't know, but we can keep in mind colloidal detachment will also go down, and we will have less erosion there. Same holds true for microbial activity. So both the pores, the small pores, and the thermal load, they will limit the microbial activity. And two examples are given here. Then same holds true for ductility. That will probably depend on the smectite content. And if we have less smectite content, or as we have less smectite content with bureau depth, that will decrease. Same as the adsorption capacity. Now coming to the swelling capacity. Well, when I started this research, I just, the first arrow we had was green like retention. So I said, well, if there's less swelling, if there's less smectite, then you would have less swelling, of course. It should translate, right? But then I found out, or I made the analogy to the bentonite research, from which is known that if you compact a bentonite, then you have a much higher swelling pressure there. So obviously we do have two effects. We have less smectite with bureau depth, less swelling, sure. But we have a higher compaction, and that translates into increased swelling pressure. That should. But as far to my knowledge, at least, there's not much published about that. What we should know to decide in which direction the arrow should go on the left side, then we should know how much percentage of smectite, like 10% less smectite, less swelling, would translate into higher swelling pressure caused by higher compaction. So different pore size, for example. But this data, as far as I know, is not available so far. And it's actually difficult to measure because you would have suitable samples, different pore sizes. They must be fresh, and the swelling pressure tests of this material are difficult. So it's a bit tricky. That's probably another reason why we don't find any data. But if anybody knows about studies, I would really be glad to have something. I was not able to find any. Looking at real data, we did not only want to do a review, but we also wanted to create own data. So we selected a couple of claystones, and the idea was to have materials from different bureau depth, of course. That was the main point. And there are some from Europe, there are also some shales from America, but we had to cancel the Wolfcamp shale because that one is actually 99% carbonate. I don't know. I lost my picture, the screen. This is actually not a shale, although it's sold as a shale, right? But we just put it aside. Looking at real data. So first, the model mineralogy. This is just calculated based on chemical composition, but this is enough to see that the variability is the carbonate content. That means in the sample set, the quartz to clay mineral content is more or less constant, right? There's a certain range, but in real systems, you will find even a more significant range. But typically, the carbonate content is the parameter which really has the highest variability in case of claystones. First, we started to consider porosity data. We used two methods. The one is the mercury intrusion that was measured by Michael at the ETH. And the other one is based on density measurements with helium and with a dry flow powder, so-called. You can see the results on the left side, and you can see that both methods are in principle applicable, right? So they're quite similar, and we are lucky with that. So we could only use one method, and we're quite sure that the porosity data is kind of significant. And then looking at the right side, we have the total porosity on the x-axis and the pore size on the y-axis. The pore size in case of claystones is actually reflecting the average distance of the particles. So it's really the main pore volume of claystones are not the pores you see directly in the SEM. It is actually the distance, or it's the space between the particles. And there are a lot of very small particles, and it is hard to resolve actually these pores, even by electron microscopy. But they make up to 80% of the pore volume. right? And by mercury intrusion, you can accurately measure this distance, obviously. And you can see here that there are some samples which do not follow the main trend. Normally, you would say that with the porosity, as we've seen before, as the porosity goes down with increasing diuria, the pore size should do as well. But the sample TS11, for example, or 12, right? They have a quite low porosity, but a relatively high pore size. So why is that? The idea was then that it could result from cementation. So we did a detailed SEM study at the University of Greifswald that was done by Tobias Menzel. And he compared, as an example, TS12 and 15. The 15 is following the trend. Pore size is much, much smaller, and the porosity is similar. So what we could see, and that was quite difficult to resolve, is that in these small pores, which are on the left side, let's take here. Yeah, this is basically the size we have to consider, like 50 nanometers, something. We could see that there are some carbonates precipitated there, and other pores were completely filled with carbonates. So obviously, this relation, the mercury total porosity and the mercurial pore size, can be affected by a cementation. Looking at clay data, we compare the specific surface area with the CEC, the potassium content, total porosity with the CEC, and these plots were not really surprising, since smectite is the main carrier of microporosity. In case of the potassium content, we think that we see more the clay content. If it would reflect illitization, then the shape of the curve should be different. And we can see that the porosity is obviously related also to the clay minerals, but this is published since decades, so there is nothing new. But it's always nice when you're investigating new sample sets to see that the data is consistent, which was published before, right? Even more important with respect to comparing claystones are the maturity indexes, the maturity proxies. We had the illite crystallinity, we had the vitrinite reflection, and the paleo-temperature derived from Rocky-Val analysis. On the left side, you can see nothing anymore. Now we can see that anymore. Again, okay. On the left side, you can see there's nothing, not really any relation. So this can be explained by the fact that the illite crystallinity of this sample set has a quite small range. It's not really, normally it's illite crystallinity is well suited until schists, right? Then the value is really going up. And in this sample set, the illite crystallinity is in a very small range. So the plot will definitely not be good. And as well, we have a geothermal anomaly for the Hills-Mulde samples. There's an intrusion next to the clay formation, and the material really experienced much higher temperatures. So that means that the vitrinite reflection is high, although the crystallization of illite did not really occur, right? If we compare the illite crystallinity with Rocky-Val, on the other hand, then this fits quite well. So that means that obviously both parameters, the Rocky-Val and the vitrinite reflection, which are commonly used to determine paleo-temperatures, they are a bit tricky. So when I look at values like 53 degrees or something, then this value is not reflecting the error. So depending on which algorithm you use and which kerogene you find in your material and you consider it with the vitrinite, you will have a significant range of paleo-temperatures. So that method has to be, the values derived from these methods have to be taken with care. And that is what you can see on the right side. That is the reason for this scattering, right? And in this graph below, you can see that a lot of scientists already found the reason. And this is actually the kerogene type, one of the reasons. There are more. Now, how to find the perfect claystones? We have not considered the pore size as possible parameter telling us something about the clay. When we look at the comparison of pore size with vitrinite reflection, we find a nice graph of the green samples, but the blue ones, they are absolutely out of the range, right? And these are the samples from the geothermal anomaly, which is quite clear. So the vitrite reflection there is high, but the burial depth was not that high. So if you have a geothermal anomaly, then you would be able to guess the burial depth from the pore size, but not from vitrite reflection. So in case of illite crystallinity and pore size, there was not a nice correlation. And in case of the pore size against rock eval, we could more or less confirm the results from figure 8 and the fact that the samples from the geothermal anomaly, they plot out of the trend. That means, and that is probably one of the most interesting conclusions of the study, the pore size seems to be the best proxy for burial depth, because it's not affected by cementation, it's not affected by geothermal anomaly, it's mostly affected simply by the load you had above the material. Up to now, we just discussed different parameters, and now the question is how to find the perfect claystone. This graph is just to show you that there are different roads, which you could have assumed, but they're equivalent. So I will not tell you that there's only one road to find an aim, right? But I will now find, let's say, or present an example how you could come to a conclusion, right? Generally, and that is out of the question which road to take, the organic carbon content should be low, because there's not any parameter which is in favor of high organic carbon contents. You have formation of gas, you have microbial activity, you have the possibility to generate secondary porosity. So that is really an issue, and it's not really a secret, because if you look at the German legislation for building the barriers for landfills, then this parameter, the carbon content, the organic carbon content, sorry, is included, right? So, and if we even use it for our landfills, then it should be possible to consider this parameter for the maybe even more important barrier, the host rock as well. But as we've seen before, not all parameters can be perfect at the same time. They go in different directions with burial depth. And that is a problem. So we have somehow to rank the parameters. And we can make use of one fact I showed before. We can reduce the parameters because some of them are obviously nonlinear, which means that, where is it here? Based on this, I will not go into the details because I had that before. Some people found that even before. Some parameters do not change significantly below a certain depth, right? And that means that we can fix them at this certain burial depth where nothing changes anymore. Still, multiple solutions exist, so there are still a lot of ways to go. So I will only, important to keep in mind, only provide an example of how it would go. And the good thing is, I don't have to take the decision, because in Germany we have the BGE. This is a big institute. They have to take the decisions. They are discussing, I guess, each day about how to do it. And I can just make suggestions, and I don't have the responsibility. That's the good of it. Okay, the example would be based on the fact that the low permeability is set as the most important parameter. That was defined just. It's not a fact that we think that permeability would be good that it should be low, right? As well as mechanical strength, thermal conductivity. Why did we put them all together? Simply because they can be fixed at a certain burial depth, right? And how deep should that be? These were the graphs I showed before. So if you look at them, we can fix them at a burial depth of 2,000 meters, for example, then the pore size on average would be below 40 nanometer. Porosity would be below 20 nanometer, and that would translate into a hydraulic conductivity of less than 10 to the minus 11, even for low clay samples, right? For a high clay sample, it would be much higher or lower hydraulic conductivity. So based on this data, we can use these plots. For example, I used the pore size, as I explained before. That is a quite neutral parameter. where this depth can be fixed, but it translates, going back, to this 2000 meter, right? So on the x-axis, these red lines I have, they represent more or less the 2000 meter, okay? So everything which is on the left side is below 2000 meter in this graph, and everything which is on the right side is higher than 2000 meter. And if we consider the CC now as well, reflecting the parameters, ductility, absorption, I showed that before, then you could even distinguish those which have a higher CC, so obviously better ductility, better absorption properties than the other ones, right? And then we would come up with this green field, and we could say the samples which are in this field, they are probably better barriers than those which are outside this field, depending on our selection of the parameters. You could do it with the paleo-temperature as well. So take the same plot, use the paleo-temperature, and you would come up with a different field now on the right side, right? If you would, of course, find samples which plot in both fields, then probably you would have something which is quite good. And if you see one of the Monterey samples is in both fields, so this is then for Nagra good news, right? No? Okay, conclusions? There's no single solution. This is what I hope I emphasized this. That was an example showing how it could go. I try to stress the importance of quality determining parameters and the importance of ranking them. We had some established correlations, including maturity proxies, which can be helped to derive unknown parameters. If you have, for example, 3 maturity proxies, you can see if it makes sense or not. This is what I showed you with the pore size. Does it make sense? The vitronite reflection against pore size against rocky vial, for example, then you can find and learn more about the material. So if you're not sure about burial depth, then you could measure the pore size as well. I know that it's the parameter which is hardly available. It's not measured very often. Porosity is measured quite often, but pore size not. Vitronite is measured very often. But if you have a site where you're not sure, then it makes sense to measure the pore size as well, to have an idea if vitronite reflection really is providing sound results or not. Okay, and yes, that's what I also said, the paleo-temperature values have to be treated with care, but they're important anyway. So with that, I thank you again. Thank you all for listening. I'm looking forward for the discussion and for any idea you may have. And thanks again for this.
Thank you very much.
You got another
No, it's fine. You're answering the questions. So,
but they have to hear you.
They do. I'll stand on my toes. Thank you. We do have time for a few questions. As with everything this week, we might hear you if you project, but for the people online, please raise your hand so we can hand you a microphone so that you can then be heard online as well. So we're making it later. Yes. First question over here.
Yeah. Yes. Thank you very much for the talk. In France, a laboratory has been built by Andra. So the claystone of this laboratory, is it in your boxes? And if it is, where is it?
It is. It's just that I didn't have the time to explain it. Actually, the values we have from Buer, they are concerning paleo-temperature. They are much higher than what was published by Andra, and we are still trying to do some let's say second or third tests on that to make sure that we didn't do anything wrong. But I can't go back to the slide. I can show you that later on, right? But we had 3 samples from Buer, and they fit all in what was published except for the paleo-temperature. This higher, we found like 80 degrees. It would be good news for Andra, I know.
Stefan, in relation to things like vitronite reflectance and rocky valve pyrolysis, they're often used in the oil industry in kind of, sections because you get lots of anomalous values. So usually when you evaluate, the burial depths that things are taken to, it might be based on a profile of vitrinite reflectance values over depth or a series of rocky val over depth. Do you have any kind of bracketing data for your organic maturity indicators, or do you just have to take single points at the moment? Because if you had the bracketing data, you perhaps could identify anomalous samples more easily.
Definitely, but for that we would need much more samples, many more samples, and even entire drills. And these were just spots, so we could not do these plots. But there would be a lot to do. So, but then we would need more time, and so that is what we could do. The study always also reflects the capacity you do have.
Question at back there and then center.
Good morning. Have any studies been done on the effect of radioactive materials on the porosity or permeability of smectites?
How many? How many studies or many studies? How many?
Have any studies been done on the effect of radioactive materials?
I'm not aware of any, but Michael, you did some, but it was not on. It was just on redox, right? On iron 2 and iron 3 and effect of iron. So I think there are more studies available of radioactivity on structural effects, but I'm not aware of any which investigates the effect on hydraulic conductivity. I'm not sure any. Maybe anyone else? I'm only aware of studies where they investigate structural degradation, possible structural degradation.
Hi, Stefan.
Hi.
In the Belgian program, there's a little bit of an outlier, as the clay they are considering, or the main clay, let's say, is boom clay, which is much more shallow than the claystones we have compared now. We're talking about 250 meters.
That's why we not included it.
Sorry?
That's why we did not include it.
How important are these, to your opinion, does the mineralogy or the clay content, does it compensate enough with respect to the other parameters that obviously are very important?
I would be incredibly brave if I would say no, definitely yes. I would not, even if you have to decide, I will have to put it in a different way. Even if you have to decide if paleo-temperature is more important for a barrier or the permeability. You cannot really decide that based on 10 years test or something like this. This is the maximum we can do. So what you would have, what you needed would be a model where all the parameters are realistic. And then you would change the parameters and see, okay, the barrier, the integrity of the barrier is more affected by paleo-temperature than by, for example, smectite content or whatever. Or it is more affected by different mineralogy. So to really take this decision, what happens after 1 million years would have to be based on a really comprehensive and realistic modeling. And this is not in sight, as far as I would guess.
Good morning, and thanks for the lecture. My question is following up on what Rico says. You have this limit of 2,000 meters where more or less is, 2,000 meters, where more or less is ideal. But we are talking about storing this waste. And the deepest mine, for example, that we have at the moment in the world is something about 1,000 meters. So like did you thought of just moving that a tiny bit and see
No,
which
no.
ones classified?
This- Sorry, that must be a misunderstanding. It is the burial, the maximum burial depth, the claystone experience.
Okay.
It is of course not lying at 2,000 meters anymore. I would not suggest to go to 2,000 meters.
Thank
So, yeah.